Hi, welcome to this lesson on the ANOVA. In the previous lesson, you learned about the t-test. With the t-test, you can compare the means between two different groups. For instance, the engagement score between Department A and Department B. What if you want to compare multiple means with each other? What if there are not 2, but 5 departments in your organization? And what if you want to compare groups on multiple independent factors? That's where the ANOVA comes in. The ANOVA stands for Analysis of Variance. The ANOVA is a great statistical tool that is used all the time by data analysts around the world. In this lesson, you will learn about 3 different variations of the ANOVA: the one-way ANOVA, the two-way ANOVA, and the repeated measures ANOVA. So without further ado, let's get started. Let me ask you a question. Why would you use an ANOVA instead of simply doing multiple t-tests? A t-test allows you to compare the mean between two groups, so if you have multiple means to compare, why not simply do multiple t-tests? This is a common mistake. The reason why we don't do multiple t-tests is due to the type 1 error. Remember when I spoke about type 1 and type 2 errors in module 2? To refresh your memory, a type 1 error is when you reject the null hypothesis, even though it is true. This is based on your alpha level, which is often 0.05. The more often you perform a t-test, the higher the chance for a type 1 error. If you do 2 t-tests, your chance for a type 1 error already goes up almost twofold. If you do 8 t-tests, your chance of getting a type 1 error could be as high as 34%. These are unacceptable error rates. An ANOVA controls for these errors so that the type 1 error remains at 5%. This will allow you to be more confident that any statistically significant result you find is accurate. To illustrate why we don't do multiple t-tests, there's a really funny comic by XKCD, which illustrates this point. Here, someone had the hypothesis that jelly beans cause acne, and after collecting the scientists and data, they found no link between jelly beans and acne. P was larger than 0.05. However, the original person had heard that the link was only between a certain color of jelly bean and acne. So they investigate and test every single color of jelly bean. Purple, brown, pink, blue, teal, salmon, red, etc. Nothing finds a link until they come to green. After green, no other color finds a link between jelly beans and acne. They've performed 20 tests and only one, green, had a p-value below 5%. Then they confidently say that green jelly beans are linked to acne with only a 5% chance of coincidence. This is true, but as they've ran 20 tests, there was bound to be one that was linked to acne purely by random chance. Even though, most likely, none of the jelly beans are linked to acne. This is an example of a type 1 error and why we don't perform multiple t-tests. Like I said earlier, I will be covering 3 ANOVAs in this lesson: the one-way, the two-way, and the repeated measures ANOVA. Let's start with the one-way ANOVA. With the one-way ANOVA, you're comparing the means of 3 or more groups. For example, an ANOVA can examine potential differences in absence rates by country, the US versus Canada versus Italy versus Spain. Specifically, it tests the following null hypothesis. HO is M1 equals M2 equals M3 equals MK. Now here, M stands for group mean and K stands for the number of groups. If, however, the one-way ANOVA returns a statistically significant result, we accept the alternative hypothesis, which is that there are at least 2 group means that are statistically significantly different from each other. At this point, it is important to realize that the one-way ANOVA is an omnibus test statistic and cannot tell you which specific groups were statistically significantly different from each other, only that at least 2 groups were. To determine which specific groups differed from each other, you need to use a post hoc test. A post hoc test should only be done when you've rejected the null hypothesis. A post hoc test, such as the Tukey's HSD test, will tell you which groups significantly differ from each other. Next, we have the two-way ANOVA. The two-way ANOVA compares the mean differences between groups that have been split into 2 independent variables. The primary purpose of a two-way ANOVA is to understand if there is an interaction between the 2 independent variables on the dependent variable. For example, you could use a two-way ANOVA to understand whether there is an interaction between training level and autonomy on job performance. This is the example we explored in Module 2 about moderation, where our third factor influences the relationship between the independent and dependent variable. Here, the independent variables are training level, high, low, and autonomy on the job, high-low, whereas job performance is the dependent variable. As you can see in this picture, training likely has a significant effect on job performance, whereas autonomy most likely doesn't. There is a visible interaction effect between autonomy and training on job performance, as there was no difference in performance for low-level training depending on your level of job autonomy, but there was a significant difference in performance for high-level training, depending on whether your job gave you low autonomy or high autonomy. This is an interaction effect, and you can use a two-way ANOVA to test for it. Finally, we have the repeated measures ANOVA. A repeated measures ANOVA is also referred to as a within-subject ANOVA. This is similar to the paired sample t-test of the previous lesson, only this time you can measure the participants at multiple time intervals. A within-subject design is a type of experimental design in which all participants are exposed to every condition. We use it when we want to measure a dependent variable, such as performance or engagement, over a period of time within the same subject group. It is similar to the one-way ANOVA. In both cases, you are comparing different means to test whether any of the means significantly differ from each other. However, we use the repeated measures ANOVA over the one-way ANOVA in this case, as it allows us to reduce the error variance, giving us more power to detect a statistically significant result, or in other words, reducing the type 2 error. For example, you could use a repeated measures ANOVA when you want to see the effectiveness of a performance review change on job satisfaction. Whereas before, you had performance reviews once a year, now you have them once a month. The independent variable here is time, whereas the dependent variable is job satisfaction. After you've collected your data, it's time to put your data to the test. With the ANOVA, we will be using the F-test to calculate whether there is a significant statistical result. This is the formula for the ANOVA. Similar to the t-test, I won't explain fully how this is calculated, as statistical programs will do this for you. But to summarize what the F-test is, so you have a rough idea of what you're testing, you're creating an F-score that corresponds to between group variance divided by the within group variance. The larger the F-score, the lower the p-value, and thus, the more significant your results will be. This isn't a purely linear relationship, as it depends on the number of subjects in our analysis, but generally, the larger the F-score, the lower the p-value. Now before you run off and do your ANOVA, there are a few assumptions all ANOVAs have to adhere to. They are: your dependent variables should be measured on a continuous scale. Your independent variables should be categorical. Remember, the one-way and repeated measures ANOVA uses 3 or more independent variables, whereas the two-way ANOVA uses 2 independent variables. Independence of observations, which means that your participants do not influence each other's scoring. If your research design is proper and the participants are randomly selected, you will often satisfy this assumption. Your dependent variable needs to be approximately normally distributed. This is not a hard assumption, as your data can deviate somewhat from normality, but the more and more skewed it is, the more you have to take the results with a grain of salt. There is homogeneity of variances. This means that the population variances in each group are equal. And finally, there are no significant outliers. Once your data adheres to these assumptions, you can run your ANOVA test. Once again, here's the picture you've grown accustomed to by now, showing you when to use which ANOVA test. So that's it for this lesson. In this lesson, you learned when to apply the ANOVA. In particular, you learned about the one-way ANOVA, which is used when you want to compare the mean between more than 3 groups on a dependent variable. Second, you learned about the two-way ANOVA, which is used when you want to see if there is an interaction between the 2 independent variables on the dependent variable. Next, you also learned about the repeated measures ANOVA, which is used when you want to compare the mean on the dependent variable over a period of time. Finally, you learned about the 6 assumptions all these ANOVA tests have to adhere to. And that's it for Module 3. In Module 3, we covered the basic statistical tests that you will use most often in your HR career. In the next module, you will learn more advanced statistical methods, such as regression. These statistics are used for predictive analytics. See you there.